Okay, everybody, to start off, how about we just pause this, take a second, like actually think, let's promote some thinking here. Get me a sentence down about what's happening in each of these three pictures here. And if you can think of other examples of this happening, well, that is just perfect by me, and we can have a talk about what's going on. Pause the video. All right, so what's happening in these pictures? Well, it appears that like our images there, whether it's our polar bear, whether it's our our ruler, whether it's our straw, whatever, it appears that these objects have been broke or they've been bent. Now, this is an example of a phenomenon we're going to be looking at today called refraction. Because what's happened here is the waves, the light waves specifically, that are allowing us to see these images, they appear to have changed the direction of where they're traveling. We don't just have this straw going straight in. It's changed direction. We don't just have this ruler going straight in. It's changed direction. And we're going to talk a little bit about why that actually happens today. Why and when waves refract, when that's happening, and how changing speed of a wave affects its direction and links together with this whole idea of refraction. So, why does it look this way? Well, we were just talking about refraction, and it's something to do with the speed. So we have our light traveling along. So we can think of those as rays traveling through the air. Yeah, these straight rays of light traveling at 300 million meters per second, the speed of light. And that's going to slow down when it approaches this water. When something slows down, it changes direction a little bit, giving us this idea that the pencil's been snapped. It hasn't been, but it looks like it has. The object appears bent because the light has been refracted as it travels into the water. And that's a really nice definition I have here. That's a magenta moment. That's something to get down. Refraction is the change in direction of light. And that is due to the change of speed that we had there. The change in speed is resulting in that change in direction. Just of the light, not of the pencil itself. The pencil hasn't changed its direction. The pencil still is where it is. The pencil's still a pencil. The pencil's still straight, right? But the change of direction of the light has made it appear to us, appear to our eyes, trying to understand the situation in the world around us. It's made it appear to us that that pencil has changed its direction. But it's just the light, not the pencil itself. So here's another example where we've got water, we've got oil, we've got different mediums, different materials, different mediums of different density. They've got different densities, and because they've got different densities, they're slowing down these light rays. They're changing the speed and changing the direction of these light rays at different rates, because we'd expect that pencil just to go straight all the way through. But it changed direction here, and then it changed direction slightly again here, because it's traveling through these different mediums, and the change in speed is resulting in a change of direction. Refraction is from a result of the change of speed resulting in this change of direction. So we can start drawing some normal lines, like we did when we were looking at reflection. The normal line being these dotted lines I have here. Let's get the highlighter out. These dotted lines I have here, an imaginary line perpendicular to the plane surface to just help give us a sense of direction, to give us an idea of where things are, to give us an idea of how we can talk about those incident rays. Those incident rays, we can still call those incident rays going in. So we have this incident ray going in, which of course is going to have an angle of incidence. And then it doesn't reflect, well, it refracts. It refracts, giving us an angle of refraction. And it bends towards the light ray. It changes direction. It moves towards the normal line. Because this block here, this block is denser than the air. It's denser than the air. So it bends and refracts towards the normal line. This block has a higher refractive index. It refracts more. Then when our refracted ray goes to exit our block and gets refracted away, it bends away from the normal. in the air as it speeds up again, as it moves from a dense subject, a dense place from being inside the block, to a less dense place of our wonderful, wonderful air, which we like to breathe. So we can think of this as an analogy. We can think of entering that glass block there, or whatever material we're talking about. We can think about this as being like a car going through mud, and the same principles apply. When a car goes through mud, when a car goes to a denser medium, it slows down and it has the possibility of changing direction. So let's look at these two diagrams in a bit more detail. So we can see actually in our diagram 1, we can see in our diagram 1 that if an incident ray goes into a material directly perpendicular and it goes straight down that imaginary normal line, it doesn't actually change direction, but it just does change speed. So that car there, it's going to be going through. It's going to slow down here, not change direction, then speed up and come out again. It's going to slow down because of the density of the medium it's entering in. It's going to refract by slowing down. It's not going to refract by changing direction. To refract by changing direction, it needs to go in at an angle. Go in at an angle of incidence, not just directly down the normal line like our example there. It needs to go in at an angle of incidence. So here we go. Our go-kart goes in an angle of incidence, and this first wheel slows down first, and it spins out and sends it in that direction. Then that first wheel comes at the air quicker, spins out and goes that direction. It slows down and it changes direction. Slows down and changes direction because it went in at an angle. We can use this car example in our brain as a model to try and think about and try and personify how the light rays are behaving. Of course, light isn't little cars driving through mud. That's ridiculous. But we can use this as a model to help us out and help manage those ideas in our brain. So here's more of those examples. Yeah, we've been talking about light all this time. It doesn't have to be light. So there we have the truck or the car example first there. We have the light example happening over there, showing us the ray entering and then the instant ray entering and getting refracted, and then another refracted ray leaving, merging and leaving. And then we also have it seen on that third example over here. We have it seen in perspective of wave fronts of a water wave, because any type of wave can be refracted. And so as this wave is moving between shallow and deep waters, it's changing speed and direction. So we're using the example of light, because light's really important because it lets us see. But we've got to think about all these sorts of wave properties can apply to actually any of our waves. It's really key. Well, here's an example for us. Because you can think about fishing. You can think about fishing. When I was in Korea, and you'll find more about my time in Korea over some lessons. I did some hand fishing. So I'm there in a river trying to catch fish with my hands. So I got something to eat. Because I need to eat, right? So there I was trying to catch fish with my hand. And you quickly learn that the fish that you're looking at isn't actually in the place where you see it. It's not in the place where you see it. Because of refraction. Yeah, we can see here, there's our actual depth, there's our real fish, and there's the image of our fish above it. So I need to actually work out, okay, what angle am I looking at this? So where's the fish going to actually be, and grab into that spot, because it's hard enough. Yeah, you actually grab from underneath and kind of tickle the bodies and you can get them. But that's a whole other video. This is about refraction. So you've got to be careful when looking at things in water to think about where they actually are. And I was having to do that when I was hand fishing. Marine birds, seabirds have to do the same thing. Yeah, seabirds, they already did this class. They know all about refraction. And so when they're flying out at sea, they're doing refraction, thinking, okay, what angle is my instant ray going at? And then where's it refracting, etc. And then they can work out where the fish is, swoop down, boom, dinner. Yeah, so they've already taken this class. So you don't want a bird to be better at physics than you, because that's really embarrassing. So that's why you get these ideas straight in your head, so you can go, yeah, I'm actually smarter than a bird, because otherwise it's, as I said, it's kind of embarrassing. So what I've got here is I've got a little word filling activity. You can just try this now using the words below. If you need a little bit of support, you can keep watching and a bit more support will pop up, and then finally the answers. But if you think you can do it right now, do it right now. You need a little bit of support, wait a little bit. You need the answers, wait a little bit more. Okay? And the extensions there describe other examples when this happens. So I've talked about some, the fishing. You could be talking about, looking through bulletproof glass or something. Things are going to refract then because that glass is so thick. Loads of examples of refraction all around us all the time. So pause this. We'll keep watching for some support. How kind of me. Here's some support. I've said which is going to be which. You just got to pick the right answer. So pause this again, crack on with it, and then we can look at the answers together. That'll be fine. Here we go. When you look at a fish at the bottom of the lake, it appears above. It appears above where it actually is. That is because the light refracts when it went from the water into the air. The light is bent away from the normal as it goes into the air because it's sped up. Refraction. Facts we need to know. Now we can even go back to the start, and we can go back to these initial diagrams we said, and we can go, hey, this is happening because of refraction, because we're entering a denser medium, we're slowing down, and we're changing direction. We should be able to say a lot more about this now than we could 10 minutes ago, hopefully. Quick fire questions. Quick fire questions. Okay, which of the following is the most dense? So which is going to make the refract the most? Lead is the most dense, but lead isn't going to be great at refraction. Why? Because it's opaque. You can't see through lead. Yeah? So the one that's going to be best at refraction is going to be glass, because that's the most dense, transparent, or translucent material we have. When light changes direction as it moves from one medium to another, we call this effect what? Refraction. Title of the video. Yeah? Okay. What happens to the speed of light as it moves from air into glass? It decreases in speed. It's moved from a less dense medium to a denser medium. It's slowed down. It's gone from driving on the road to driving through mud. It slows down. Refraction. Facts we need to know. Here we go. If a ray of light moves from air to glass parallel to the normal, what happens? No change in direction. So remember, that's your time with refraction, where direction does not change. No change. Think of the car, goes straight to the mud, doesn't change direction, still changes speed.